Everybody, this is the lecture for fluid mechanics in the series of fluid mechanics Purgate and ESE examination. So in this lecture, we have concluded the last chapter, that is chapter number 1 in the previous videos. So I've taken a break after completing that chapter for 4 to 5 days. So now I am going to start a practice set for chapter 1. So in the last lecture we have studied about uh, uh, how to find the flow patterns, or how many types of flow patterns are there. So now from this lecture we are going to solve some problems. Okay, so maybe in the continuous I will in this chapter I will make 4 to 5 more videos for problem solving only. Okay, so in this lecture I'm starting with some important points to note. I'm just writing the statement that can be very useful for understanding the concept of fluid mechanics, as well as especially during the solving the problems like which are objectives and come in competitive examination like GATE or ESE. So the first point to note here is, yeah, so the first point to note is that for static fluid. Okay, so remember, for static fluid the fluid which are having rest and which are in equilibrium, that is net force acting on this static fluid is zero, right? So that's why I've written here static fluid, that is bodies of the fluid is at rest or has zero velocity. Okay, that means the fluid body are having zero velocity. In that case the shear stress is always zero, right? I've told you earlier, right? Whenever the shear stress is zero, that means the fluid is in static condition or in the rest condition, right? I have discussed this earlier in the video, but I'm just revising the things. Okay, for the second point we have written, for static fluid normal stress is always positive. Okay, for static fluid normal stress is always positive. So in the first this question we will discuss about normal stress and shear stress. Just remember the point that for static fluid normal stress is always positive. Okay, so just remember that. Okay, so these 2 points are very useful. For this practice at 01, I will make I maybe take till 5 or 6 practice at 5 or 6, and after that we will just quickly discuss about previous year questions of the fluid mechanics, and basic of fluid mechanics, and then we can move quickly to the chapter 2. Okay, so first we are going to discuss problem number set 1, and the problem number 1 is a force F1 is applied on an area A1, that is 0.1 centimeter square, at the surface of a fluid element in the outward direction. Okay, so it's saying a body is there with area A1, a force is acting this one F, and the value of F1, I'm writing it as F1. So the first force, and the magnitude of that is 20 Newton, and the area over which it is acting is A1, and that is 0.1 centimeter square. Okay, and the force F1 acts an angle of 60 degree from the tangential plane at a point of application of the force. So this is the point of the application of the force, and this is the tangential plane, right? Ft, that I have denoted here Ft, and the perpendicular is of that Ft is Fn. So the angle making uh, with respect to Ft of F is 60 degree, right? As it is mentioned here. Now another force F2 is applied in the same manner as the F1. That means another body is there with the area A2, and in the same manner another force is acting F2 with the tangential plane of angle 60 degree, and another perpendicular force, that is normal force F1. Okay, so both the condition are same, that's why I written here, and the value of A2 is 0.2 centimeter per square, and the forces now acting is 60 Newton. Okay, at the surface of the same fluid element. The ratio of the normal stress at the area A1 to the shear stress at the area A2, right? In the previous point I have told you that I will discuss what is normal stress and shear stress for a fluid element. Okay, so I have discussed here. Let's suppose a body is there and a force is acting here F. Okay, some point of application force is there F. Okay, and so you can you can resolve this force F into two perpendicular direction. One is like For reference, we take it in a horizontal force, horizontal plane, and that we will take as a ft, tangential force component, and one is in the perpendicular direction, that is and normal force acting. Okay, and the relation could be easily established like, see, ft divided by a is equal to f cos theta divided by a. That means if you resolve this force in this horizontal direction and tangential direction, you will get f cos theta, right, and divided by dA. Both are equal, right? If you cut dA, nothing will get changed. Similarly, for in the case of normal forces, just keep it f sin theta. Okay, so this one is normal, tangential force, and this one is normal force. So if you, for normal stress, we don't treat it by sigma. Now you have to do is f n multiplied by dA, right? And for shear stress, you have to multiply the tangential force with this area, and this will give you normal and the tangential force. This one is normal force, this one is tangential force, or the shear force we call it. Okay, and now for shear stress, sorry, now for the area A1, what they are asking is the ratio of normal stress at area A1. So for area A1, we have to find out the normal stress, right? So we have to take the component of Fn1, right? So we will make it Fn1 divided by A1 equal to F1 sin 60 divided by A1. So A1 get cancelled, so Fn1 is equal to F1 into sin 60 degree, that is root 3 by 2, and F1, and the value of F1 is 20 Newton given there, right? So we will cut it as a 10 times, so 10 root 3 Newton is the value of normal force for area A1, right? Now similarly, we will move to the for area A2. So for area A2, they are asking shear stress at area A2. So we will find out tangential force, right? And that could be easily written as, I'm sorry, not in this case here. D will get cancelled. So Ft is equal to F cos theta. So F cos theta, F is given here F2, that is 60 degree. F2 is here 60 degree into cos 60 is 1 by 2, right? So it will become 30 Newton. Now required ratio, the ratio that they are asking is normal stress of 1 and the shear stress of 2, right? So we have taken the ratio of normal stress of area 1 and the shear stress of area 2. So what we will do for normal stress of area 1 is F1 normal force divided by A1, right? The force divided by area is stress. So this is the normal stress, and this one is for shear stress, right? And the ratio of both is taken here. And for F1 we can write, we found out that 10 root 3 is the value. Area of 1 is 0.1, that is given there, so 0.1. A2 is given 0.2, so 0.2, and Ft2 is 30 Newton, right? So 10 3 is 30, and 0.1 to the and root 3 times 3 is root 3, right? So that the answer would come 2 by root 3. So the option C is correct. Okay, so I hope you all are clear with this question. Now the second question is, it's a very simple question, like one word question. The question says an example of a normal stress is, so the normal volume, no, it's not to deal with the any force or stress. So it's not. Shear stress is obviously not a normal stress, right? Shear stress and normal stress are both are perpendicular to each other, and temperature is also not a force or stress, right? We can simply take the pressure as the answer. Okay. Now, the question number third says an area of 0.1 centimeter square at the surface of a static fluid element, a force of 40 Newton is observed to act in the outward direction, right? 140 Newton force is acting outward, right? If the force acts an angle alpha from the tangential plane at a point of application of the force and the fluid still remains static, then the value of alpha is. It's saying one force outward, acting 40 Newton in outward direction with the angle of alpha with respect to the tangential force. Okay, so they are asking at what value of alpha that so that the fluid becomes static. So for static fluid, we know that shear stress would be equal to 0, right? I have told you here in point 1 for static fluid, the stress is always 0, shear stress is always 0. So we will take the shear stress to be always 0. The shear stress can be given as F cos theta, which can be Ft, and divided by this we will get a shear stress. We have discussed here, right? We have discussed here in detail. So Ft divided by A should be 0. We know that F is not 0, A is not 0. So for that, cos alpha should be equal to 0, right? This is the only condition that we can satisfy here. For that, we should know that alpha is equal to 90 degree, it will be 0, right? Cos 90 is 0, so we are taking alpha as a 90 degree is our answer, right? Okay. Now we will move to question number 4. The question number 4 says a specific weight of a body of a fluid A is 12 times the weight of the body of B. That means the specific weight of A is 12 times the specific weight of B. The acceleration due to the gravity acting on fluid A is 4 times that acting on the B. That means the acceleration at A, we can write it as G because it is given acceleration due to gravity. Okay, so G of A is 4 times of G of B, right? It's given A. If the specific gravity, that means rho density of a fluid is 1.2, that means rho of B, right? Fluid B is given as 1.2. Then the density of A, so they are asking the density of A, what it should be, right? So we know the WFA, that means the specific weight of any fluid is given as weight of that fluid divided by volume, and the weight of the fluid written as mass into gravity, right? Divided by volume. Mass divided by volume is known as the specific gravity or the density. So the specific gravity, a specific weight of the any fluid is given as a specific gravity into gravity, right? WA by WV is given as 1.2, sorry, 12, my bad. Okay, you are 12, and so WA can be written as rho A into G, right? We have established here that WA is equal to rho into G. We have written here rho A into G divided by rho B into GB equal to 12. So rho A, we have I mean, in the left hand side, I just kept row A because we have to find that only, and all other things are sent to the right side, right? So 12 into GB by GA, right? Here it is denominator, here GA is in numerator. So by keeping it in the right hand side, it will become GB divided by GA, right? And rho B in the numerator again. So 12 GB by GA is GB by GA, that means AB by A, right? So that can be written as AB by A, and that can be written as 1 by 4, right? From here. So we have written 12 into 1 by 4, and the rho B is given 1.2. So 4 3 is 12, and 12 3 is 36. So we will write it as 3.6 is your answer, right? So the option B is correct. Now we will move forward to question number 5. So question number 5 says when two immiscible liquids A and B are poured into a cylinder container, then these separate out into two distinct layers of different heights as shown in the following figure. The specific gravity of liquid A is thrice that of the liquid B. Okay, so they are saying two liquids are there that are immiscible. They're forming a layer in between of them, and the upper layer is fluid B, and the bottom layer is fluid A. Okay, and so given that the specific gravity of A is thrice of the specific gravity of B. Okay, and also it is given that ratio of HB by HA is 2:1. Okay, so they are asking MA by MB, sorry, the ratio of mass of liquid A to the mass of the liquid B, that means MA by MB, they are asking, right? So now we will see by the concept of a specific gravity. Already we have learned in the lecture, so I'm just explaining it quickly. A specific gravity is defined with respect to any reference fluid, right? So here we have written a specific gravity of any fluid is a weight of that fluid with respect to the some standard fluid, right? So now for SGA by SGB, we can write it as MA into GA, that is weight can be written as MA into GA divided by VA, right? This is only a specific gravity that we have discussed here. Sorry, specific weight here, W, right? So same formula applied here, MA into GA divided by BA. And for SGB, MB into GB divided by BB, right? So specific gravity, gravitational value will remain same here. So we have cancelled GA by GB. So now the we know that SGA divided by SGB is 3. MA divided by M, we have to find it out, and volume of this area A, or the volume of fluid B, can be written as cross section area, that this one into height of A, and for volume of fluid B, it can be written as cross section area into height of B, right? So that's what I have written here. For BB, I have written A into HB. For BB, BA, I have written A into HA. So A get cancelled, cross section area will remain same for liquid A and liquid B, right? So we have cancelled both the areas, and the value will remain here HB by HA. So now HB by HA is known, that is 2. So we keep it as a 2. Now the MA divided by MB, that question has asked the mass of liquid A to the mass of liquid B. So this we can write it as 0 by 2, right? After sending 2 in left hand side, so MA by MB is equal to 3 by 2, that is 1.5. So this is our answer. Okay. Now one more question is there, that is question number 6. And the question number 6 is a gas behaves like a real gas at temperature T1 and pressure P1. The gas can be made to behave approximately like a ideal gas. Okay, so a real gas is there. I mean, real gas, for example, you take it as air or anything kind of thing. Okay, so and it is at pressure P1 and temperature T1, right? And now it is saying, so saying that after changing temperature something to T2 and pressure P2, after changing this temperature and pressure, it behaves as ideal gas. So which of the option is correct? Okay, so we will go with the concept that we have studied, and that for any fluid at low temperature, sorry, at high temperature and low pressure, okay, we can approximate a real gas to ideal gas, right? We know that. So for any real gas to convert it into an ideal gas, the pressure should decrease, right? So P2 will be lesser than P1, and for T2, that higher temperature, right? That means T2 should be greater than T1. So when temperature increases and the pressure decreases, then can real gas can behave as an ideal gas, right? So this option will match and our answer will get corrected. So this is option number A, right? T2 is greater than T1 and P2 is less than P1. Okay, so this is the correct answer. So that's it for today. So the practice session 1 is getting completed. So in the second lecture, in the second lecture of the for the practice session, we will discuss some problem related to viscosity and the steps. Okay, so till then, keep learning and good.